In the last video, we introduced the concept of torque, a force that causes rotation. In this video, we will apply this concept to statics puzzles, a class of puzzles that has many important applications, particularly in mechanical engineering. Statics puzzles are a class of puzzles in which an object is standing perfectly still and unmoving. There are two conditions required for this to occur. First, the total force on the object has to be zero to prevent linear acceleration. And second, the total torque on the object has to be zero to prevent angular acceleration. Let's apply this to several examples. Here, we see a 20-kilogram seesaw that isn't moving. There are two objects on it, a 1-kilogram object at left and a 4-kilogram object at right. The 4-kilogram object is 0.3 meters from the fulcrum. What is the normal force on the seesaw, and how far is the 1-kilogram object from the fulcrum? To solve this, we first set up a force balance. The total force on the seesaw equals the normal force pointing up minus the weight of the seesaw, the weight of the 1-kilogram object, and the weight of the 4-kilogram object. The sum of all four of these forces is 0. The weight of the seesaw is calculated using W equals mg. It is 196.2 newtons. The weight of the 1-kilogram object is 9.81 newtons, and that of the 4-kilogram object 39.24 newtons. So the total downward force is 245.25 newtons. And since, in the definition of a statics puzzle, the total force is 0, we can easily find the normal force. It is also 245.25 newtons. Now, to solve for the distance from the fulcrum to the 1-kilogram mass, we need to solve the torque balance. The 4-kilogram mass exerts a weight of 39.24 newtons. The force is located 0.3 meters from the fulcrum. The angle between its weight and the lever arm is 90 degrees. So its torque is 0.3 times 39.24 times the sine of 90 degrees. That works out to 11.772 Newton meters. This torque would tend to push the seesaw clockwise, so correctly we should say it's negative 11.772 Newton meters. But that's also why I wrote the torque balance with a negative sign. The total torque in a statics question is 0, so the torque of the 1-kilogram mass must balance out the torque of the 4-kilogram mass. The torque of the 1-kilogram mass must be positive 11.772 Newton meters. Since the weight of the 1-kilogram mass is 9.81 newtons, and the angle between the weight and the lever arm is 90 degrees, we can work out the 1-kilogram object has to be located 1.2 meters from the fulcrum. The same logic applies when the seesaw is tilted like this. The forces are exactly the same as before, but because of the change in angle, the torques are different. The torque of the 4-kilogram object is now equal to 0.3 meters times 39.24 newtons times the sine of 60 degrees. That works out to negative 10.19 Newton meters because the torque is still clockwise. Meanwhile, the torque for the 1-kilogram object is now 1.2 times 9.81 times the sine of 120 degrees, which works out to positive 10.19 Newton meters. Notice that even in this tilted position, the torques cancel each other out and the total torque is still 0. There's a class of torque puzzles called statics puzzles. In a statics puzzle, an object is not moving. For this to occur, all the forces need to add up to 0 and all the torques need to add up to 0. Here we see a 3-meter 15-kilogram ladder leaning against a wall at an angle of 50 degrees. The wall is frictionless, but the ground is not. The ladder is not moving. It feels four forces: weight, normal from the ground, friction with the ground, and normal with the wall. What are the values of the two normal forces and the coefficient of friction? The first step is to fill in some more details about the drawing, the sizes of the angles and the locations where the forces are acting. Remember that the sum of angles in a triangle is 180 degrees, and that weight always operates at the center of mass. I set the origin where the ladder touches the ground. I'll explain the logic for this in a few minutes. We'll start by setting up Newton's second law for the y direction. There are two forces acting in the y direction: the normal force from the ground pointed up and the weight pointed down. Since the acceleration in y is 0, these two forces must cancel out, and so we can calculate the normal force from the ground. Next, the x direction. Static friction points right, and the normal force from the wall points left. These also cancel out to 0, but there are two unknown variables: the normal force from the wall and the coefficient of static friction. So next, we have to do the torque balance. There was a reason why I placed the origin at the left corner. It's because the origin always is located at the center of rotation for torque, but if the object isn't rotating, you can consider any location to be the center of rotation, so you can put the origin wherever you like. At the left corner, two forces would pass through the origin, or the center of rotation, which means their lever arms are 0 and they will exert 0 torque. So the only torques to worry about are from the two remaining forces, weight and the normal force from the wall. We can find the torque from weight by multiplying it by the lever arm, in this case 1.5 meters, times the sine of 40 degrees, since that's the angle the weight force makes with the lever arm. This is a clockwise torque. We can find the torque from the normal force at the wall similarly. This is a counterclockwise torque. These torques must cancel out. A little algebra will tell us the size of the normal force and the minimum value of the coefficient of static friction. If you could solve this, try doing the puzzle with an 80-kilogram person standing on a rung 0.5 meters away from the base of the ladder. If you can do that, then puzzles like an unmoving seesaw or a person standing on a suspended scaffold would be a piece of cake for you. This video introduced torque and explored Newton's second law for rotation. We went through several sophisticated puzzles. Next time, we will examine how energy and momentum play into rotation.